Hello and welcome to Easy Projects. Today I'm doing a Christmas special where we will have a hack at this Christmas tree. Well, it is a nice tree, but that lighting pattern is very distracting. Imagine having that in a dim living room while trying to watch a movie or read a book or something. That is just impossible. Perhaps it would be great in a nightclub, but I think that's all it's good for. So I want to have a look and see if we can do anything to the lighting pattern, slow it down or maybe change something to make it a little more useful. At first I actually thought all these lights were LEDs, but then I noticed that down at the base here there's some light coming out of the top plate. And you might just be able to see that there's a spinning disc over there. So how this works is they got a halogen light bulb that shines through a colored disc, and the disc is just rotating. So I was thinking about slowing down the motor or doing something like that, but we'll have to take it apart to see what we can do. So all these are actually fiber optics, and the bottom of the tree is actually made up of all these fiber optics that have been cut flat here. So it is a rather clever design, I think, but it must be a very expensive way of doing it. So there's not much else to say about this base. We have the motor in here, and we can see the disc I was talking about before. It sits in the middle here, and of course the tree goes down this hole. And with the different patterns on this disc, it will shine different color light into the different fibers. So let's open it up. And here we have it. So this might not be as easy as I thought, because this is a synchronous AC motor at the 12 volts AC. So I don't know why I thought it would be a DC, just because it came with one of these wall adapters, because that actually also confirms that it is AC. So, well, it is not impossible. We will just have to alter the frequency of the drive signal in order to change the speed of the motor, because the speed is synchronized to the frequency. So I think we'll have to build a variable frequency drive for this one, and we have plenty of room here, so I think we can make it fit in there. I will just unplug the light bulb here, because that's powered from the same set of wires, so we don't have to power that while we do the testing. So it is actually a shame that we have to make this motor go slower, because that is a problem with these synchronous AC motors. I have drawn a very simple example of this type of motor here, and I'll try to explain how it works. We have 2 or more coils, and we have a magnet in the middle with the same number of poles as we have coils, so in this case we just have one north and one south pole. So when we put an AC sine wave into this motor, at one of the peaks we will have a north pole here, a south here, a north pole here, and a south pole here, and of course only the 2 in the middle are relevant. That will of course attract the opposite pole on the magnet, so that will be orientated like this. So when the polarity of the sine wave switches around, we'll get a north pole here and a south pole here, and the magnet will rotate. One of the problems with a motor like this is if the magnet is positioned like this one, you have no idea if it will turn to the right or to the left. So you don't know which way the motor will start up. But when it is going, it will keep going the same way around because of the momentum of the magnet. So if we imagine that the motor is at a standstill and the magnet is positioned like this, and we start with the south pole here, it will start to rotate that way. But if at standstill the magnet is at this position, it will start that way around. So if you imagine that we drive this at 1 Hz, for example, normally it's driven at 50 Hz and that works just fine, but if we take 1 Hz, we start like this and the sine wave switches around, the magnet will take 1/2 of a turn and it will stay there until the sine wave switches again. But we don't know if it will take this path or this path. So it could actually just be going like this. And maybe sometimes it will take this way and back again. So we have to keep this magnet moving in order to make the motor run. So I have no idea about the lowest frequency, but I guess we'll find out. And another thing, this is driven by a sine wave normally, but I think we'll find it easier to generate a square wave. So we'll have to see if that works as well. But in practice the motor will look more like this, because it will have more coils and more of these poles around, perhaps even more than I've drawn here. Sorry about the bad drawing, but this is just to illustrate that on this motor, for each half period of the sine wave, it will only travel this far compared to a half turn on the other motor. But we still have the problem, if the motor is staying still, it could go this way on the next half period of the sine wave. But if we have a little momentum on the rotor in here, it will keep going this way. But if I went and physically stopped the motor, it could start going this way. And it will keep going that way until something stops it, or you cut the power and power it up again. Yeah, and enough about that. Let's get on to the variable frequency drive. And I'm planning to use a circuit from a previous video I made about the 4069 inverter chip. And we can use this to generate a clock signal, and we can make it variable by adding a pot here. And if you want to know how this works, I already explained it in the chip chat video about the 4069 chip, so you can go and search for that one, or I will add a link here. That would be easier. So if we were to build this circuit, we would get a square wave on the output that we could adjust in frequency, but it would have a peak-to-peak voltage of 12 volts, because we have or it would be 16.8 volts, because we are of course rectifying the AC signal, and the AC RMS is 12 volts, so we will get 16.8 volts DC. But on the 12 volt RMS sine wave, we will have a peak voltage of 16.8 volts DC. But the peak to peak voltage will be 2 times that. So we will have to do something about this signal to get double the amplitude. And we can do that with a H bridge. So if we add this to here, it would look something like this. Oops, I need a resistor here. So if we add this to our inverter, it could look something like this. where we have 4 transistors, 2 PNP and 2 NPN. And the way it works is this signal will of course go from 0 volt to 16.8, and it will alternate between those two. And as you can see, at 0 volts on this node here, current will be able to flow through this transistor and through this transistor. And this one is connected to 16.8 volts and this one is connected to ground. So this means that current can flow down through this transistor, out of this node, into this node and to ground. And when this one is at 16.8 volts, this transistor will be turned on and this transistor will be turned on. And as you can see, it have flipped around, so now we can send current through this transistor into this node and down to ground. So if we had 16.8 before, now we will have minus 16.8. So that also gives us a peak-to-peak value of 16.8 times 2. So now we just have to build all this stuff up, because I don't know if it will work with an AC synchronous motor when it's square waves. I know that this system will produce the 33.6 volt peak-to-peak square wave, but you'll have to check if the motor will take that. And then we can check how low we can set the frequency, and the motor will still operate. So here it is, and I'm sorry it looks like a mess, but here are the 4 transistors and the 4 resistors. I got my part here, and if you want to see anything about this circuitry, you can look up my previous video, as I said before. So I'll just connect everything up and let's see if it works. Alright, so it seems to work just fine, so let's try to change the frequency. And as I already guessed, it can go much faster than the 50 Hz, but let's try to turn it down. Let's see. Yeah, it goes slower than the 50 Hz, but let's see when it will stop. Oops, as you saw, it just started to turn the other way around. And it's just oscillating, so that's too slow. Let's try to turn it up a little bit. Oops, I'm turning the pot the wrong direction. And there it starts to work again. So let's just check what the frequency is. So the scope is saying 30 Hz. That was a little higher than I have hoped for, but I guess there's not much to do about it. Let's see how fast it will go. Oops, wrong way. And here we have 187 Hz, and I guess it could actually go faster than that, but then I would have to change the part. But anyway, the aim was not to make it go faster anyway, so I guess that's just fine. Let's just double check the lowest frequency. And as you can see, it at 28.5 Hz, it just stops. And 29 point. It's not going yet. Yeah, so 30 Hertz is about the lowest we can make this go at. So these transistors are getting a little warm, so either I should put some larger ones in, or I should just add a little heatsink, because it's not that bad. I'd say about 55 degrees or something. But let's just measure that to be on the safe side. I think this one is the one getting hottest. It's not gonna stop at 55. I guess it's because it's so small, you can't really feel it. Almost 70. Yeah, we have to do something about that. Yeah, it is around 70-71 degrees. I mean, it's not too bad, but there's also the halogen light bulb in the lamp that will also produce some heat, so I think it would be better to add a heatsink, or change it to the BD139 and the BD140 transistors instead. They can take a little more power. So, as you can see, I went and changed the transistors to a more power-friendly type, and they're not getting warm yet. So I will let this run for a couple of minutes and I'll come back, and you can see it's still running, and I have checked it, the frequency is still the same. It will go to 187 still. I expected that, but I was expecting that it could affect the lower frequency, because if these transistors doesn't have the same gain, it could kind of affect the current a little, but it seems like it's running just fine. And I will set it at 30 Hertz. That was where the other transistors were getting hot. Yeah, I would say this one is about 50 now, so 47, but we will just leave it for 15 minutes and I will come back. So it's been about 15 minutes now, and the temperature have settled around 55-56 degrees. And I'm measuring the temperature of this one, and that is the one getting warmest. This one is almost as warm, and these two are a little cooler. So 56 degrees, I could live with that, but I think when we put it into this enclosure here where we have the halogen light bulb, it would rise a little bit, so I'll add some heat sinks to the transistors. And that is also a lot easier with that type than if we have a package like this, because there's a screw hole in these. So now I will just have to put this on a PCB and add a rectifier and a few filter capacitors. But unfortunately the smallest rectifier that I have is this one, and it's too big, so I'll just add 4 diodes to the PCB instead. So we can make a rectifier by putting 4 diodes in this configuration. And that's exactly what is inside one of these. So we will connect the wall adapter to these two nodes here. So when the sine wave is high on this node here, current can flow to the positive, back into the negative, and to the other terminal here. And when this node is negative, then current can flow in through here and back up to here. So this will take a signal that looks like this into a signal that looks like this. But we will need to smooth this out, so we will just add a large capacitor across here. And that will make this flat at the peaks of this signal. But as we use current from this, it will only be charged up at the tips, so it will look something like this instead, but we can accept that. So I have finished up the board here, and now we just have to make a test to see if it works. So I have just hooked it up to the power supply here, and it's drawing about 6 milliamps, so nothing is shorted at least. But let's try to do some measurements with the scope. So let's check the output of the inverter chip to see if we have an oscillating signal. And we have. So the next thing should be the outputs of the transistors. We can check that here. And that one's working. And that one's working as well. So it seems like it's working just fine. But I just noticed one thing here. I have my wires for my potentiometer here, and I've got the input here. I haven't soldered those in yet. And where should I plug the motor in? Oops, fail. Forgot to add the pads. That's what happens when you make things in a hurry. Oops. So, problem solved. Well, it ain't pretty, but it will have to do. So I've got everything connected up and it is working. I only had one problem because every time I connected this motor it just shorted out and I could not find out why. And guess what? Because I put the light bulb in when I had to take measurements for the board. Fail! So I just had to scratch my head for 10 minutes there. But everything left now is just to desolder the wires to the motor and connect them to this board instead. So the lamp will be powered directly from the input and the motor will go through the board. So I will quickly do that and we can put it all back together. So now everything is put together and we just have to see if it works. And it does. So now my only concern is if this transistor or these transistors will overheat. So we'll just do a little measurement of that. Oops, I need to change the battery, but I guess that can wait. And I think we'll leave it for about half an hour and come back. So it seems to have settled around 67 degrees and I think that's acceptable. Even if it should go to 75, that's not a problem either. So, but I think it is as warm as it will get, so I'll just leave it at that. So in the beginning I mentioned that this would be running at 16.8 volts. And of course that is not a good idea when the chip is rated for 15 volts. So let's just check the voltage on that chip, shall we? We of course have these diodes here that I did not take into account, and also the light bulb will make a voltage drop on the transformer. So let's check. I already checked this of course, but I just want to show you as well. And how lucky can we be? It is 15.4 volts. And the chip is rated for an absolute maximum of 18 volts, I think it is. So we can live with that. And even if the light bulb should go out, it will go up to around 16 volts. So that's still within the absolute maximum. But I should have thought of that. Oops. So it is all back together now, and I think it is a little bit less annoying. This is at the lowest speed, but I think I can live with that. At least now I can choose if I want to be annoyed at 30 Hz or at 180 Hz. Now, ain't that cool, huh? So that was all for this time, and if you liked the video, please give it a thumbs up and subscribe to my channel. And Merry Christmas!